The Student ODEs package was introduced in Maple 2021, but in Maple 2022, access to its functionalities was provided through the context panel, making the package syntax-free and clickable. So this webinar takes a brief look at the tools in the package, but illustrates them via a collection of examples implemented in a syntax-free way. It's this freedom from the constraints of syntax that makes the Maple 2022 version truly student-friendly. To make use of the tools in this package, you need to bring it into memory. You could use with Student ODEs. You get 13 commands now available, each with its own syntax and options. Kind of hard to access this material without the tools being put into the context panel. Let's take a quick look at what's available in this package. Now, the first 7 of these commands: change variables, differential order, integrate, integrating factor, isolate highest derivative, linear form, ODE plot. It would be difficult to learn the syntax of each of these commands, and students are just not going to absorb all of that information. There are 39 separate help pages for all of this information, and the expectation that a student is going to rummage through 39 different help pages to see the syntax of something, I think is unrealistic. And it is only by doing this in a syntax-free way, and you'll see how much simpler it is momentarily. The next command, ODE steps, subdivides. The package provides, or this command provides, stepwise solutions to each of these items. Cauchy-Euler equations, first order initial value problems. First order, you're going to get general solution. Second order initial value problem, second order general solution. Series, solutions that involve special functions like Bessel functions. Systems, clearly linear systems, and linear systems posed as initial value problems. You get stepwise solutions for each of these. Much simpler to just access from the context panel. The next 2 commands, reduce order, separate variables. I've grouped those together. Reduction of order has 3 cases: linear particular solution, no dependent variable, no independent variable. I can remember these topics from my old Rainville differential equations book that I used 50 years ago. More like 60 now, I think. Okay, and then separating variables. This was always a hard thing to do in Maple without any special tools. To separate variables in the differential equations and then integrate both sides, it took a lot of finesse at the keyboard, and now there is a command for it. The next command in this list is the solve command, and it has all of these subcases. If an equation ends up with Bessel functions, you can solve by Laplace transform. You get a perturbation solution, a series solution, undetermined coefficients to get a particular solution, variation of parameters, but that applies to a linear system. Cauchy-Euler equation, the Chebyshev equation, exact equations, first order equations, first order linear, higher order, linear equation with constant coefficients, second order, separable equations, systems. So applying solve to a differential equation, if you know its special category, you get wonderful properties. But to keep track of the syntax of all of these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different categories, that's why there are 39 different help pages. So I will show you shortly examples where you just go to the context panel and the appropriate option is there in the context panel. Click on it. You don't have to know the syntax. The final two commands that you have access to are test and type. Now, these were available outside the package earlier in earlier versions. Test is the ODE test to see if something that you think is a solution satisfies the equation. Type is the command that tells you what kind of equation you have. But here it's determining whether an ODE is separable, linear, or exact. I've got some 14 examples that I've prepared. I'll see how many of these I can take you through. The first one, separable ODE. And we're going to be working with the context panel, so I think I'm going to just leave it open. Here's a differential equation. Notice the stage directions. Student ODEs. Separate variables in Z. It gives you this line. Student ODEs. Integrate. Now you got two things you can do. You can integrate directly, which is what you see, or you can apply the integrals as inert integrals so you can see what's happening to each side of the equation. If you have the inert integrals, then you can evaluate them. Student ODEs. Integrate, evaluate. So we didn't need any of the commands. We simply used the context panel and what it provided to initiate the actions that we wanted. The second example is an exact equation. You can find out if it's exact. Student ODEs, type, test if exact. If you want to integrate it, you can do it directly, or you can do it with inert integrals so you can see what the integrals are. If you want a solution, pick solve. And on the generic, you have these options. Just give me the general solution. Or you can get the general solution stepwise. Had we picked general solution with steps, we would have obtained this stepwise version of the solution. I think it's a pretty amazing piece of work here. It analyzes the differential equation, checks for exactness, illustrates what that test for exactness is in this differential equation, implements the steps of not only the test for exactness, but what you do when you discover that the equation is exact, and then it provides the solution. And so the way you would get to this is simply through that context panel. Third example is differential equation that has an integrating factor. So let's take a look at this differential equation. Here's the differential equation. Student ODEs. Integrating factor. Maple provides an integrating factor using the ordinary tools here in the context panel assigned to a name. Give it the name mu. Now, this is the product of mu with the differential equation. Any place there was a command, standard command like that product, it's behind the cell. If you bring up the table properties and show input, you would see what took place behind mu times the differential equation. Okay. Student integrate. This is integrate inertly. This is the active. So that produces the solution. Give it the name SOL. And then if you want to test if that solution satisfies this differential equation, Student ODEs, under solve, you have that test option. You get this pop-up. You type the name of your candidate solution, and you get back an indication that this is indeed a solution. Example 4. A first-order equation posed as an initial value problem. So here's the differential equation, initial condition. Differential equation, student ODEs. I'm going to go to solve, generic, with steps. Okay, let's take initial value problem with steps, and this is what you get back. You get a list of the steps. Okay, so the differential equation is analyzed, turns out to be variable separable, both sides integrated, evaluate the integral, apply the initial condition, determine the arbitrary constant, put the arbitrary constant back in a statement of there's the solution. It only took the use of the context panel. It did not require that the student look up syntax for how to solve the problem or see the steps. They simply make the selection from the context panel and don't have to dive into any of the help pages to look for the appropriate syntax. For a fifth example, we have a second order differential equation posed in an initial value problem. So here is the differential equation. Here are the initial conditions. When you go to the context panel and you pick Student ODEs, Solve, Generic, Initial Value Problem with Steps, pick Y of T, you get a dialog box where you put in the initial conditions, and here I show what you have to type for the initial conditions. Now, this is a bit awkward to type, and MapleSoft has been advised that there is simpler notation, and that's being worked on. So, the stepwise solution, here's the problem being solved. Maple puts the equation in an order that it prefers. Characteristic equation, characteristic roots, they're repeated, minus 2 root is repeated. Here are the two members of the fundamental set, e to the minus 2t, t e to the minus 2t. General solution, now we need to get a particular solution. Maple finds a particular solution by variation of parameters. This is the Wronskian. What is the Wronskian? It's the determinant of this matrix. So it turns out to be e to the minus 4t. There is the particular solution. Compute the integrals yp. So now you can write down the general solution. Two constants defined, use the initial data to find it. You apply the first condition, y at 0 is 1. You take the derivative, you apply the derivative condition. You've got two equations to solve for the two constants. Here are the values of the two constants. You put them into the equation for the general solution. You've got the specific solution to this initial value problem. Maple decides here it wants to check the validity of this general solution, and this statement saying the constants are all equivalent is its way of making that check, and it finishes with the solution to the initial value problem. The sixth example has us solving an initial value problem by the Laplace transform. This is the initial value problem. Here is the equation. Let's go here to the student package. You would pick solve Laplace transform, and you have this pop-up, and you notice here where it says steps, here it's a solution, it's a drop-down, you pick steps, and then you enter this set of initial conditions as you see here, and then you get back a stepwise solution. So Maple says we're going to solve this problem. It lets the forcing function be f of t for a while. It says the transform of little x is big X of s, applies the transform to both sides, breaks it up by linearity. It takes the transform of the first derivative, then the second derivative, puts it together, applies the initial data, collects terms, and solves for x of s, and it keeps two separate pieces and calls this the piece for the homogeneous equation and this from the driving term. So now it looks at the equation and says we'll invert both sides. So it's simply applying the inverse transform to both of these pieces and says when you invert big X of s, you will get little x of t, and you have to invert these two pieces. So then it turns its attention to inverting those two pieces. It splits them, and it says first calculate the inverse of the homogeneous part. So you have this fraction here, and it's going to do the inverse with pencil and paper techniques. It's not going to call partial fractions decomposition. It's not going to call inverse Laplace. It's going to do it in terms that one would have used 100 years ago with pencil and paper. So it looks at this fraction, completes the square in the denominator, then rewrites it as two separate pieces, which is really partial fraction decomposition. Looks at the first fraction, and it inverts it using this rule, and so it gets this piece. Then it looks at this fraction, and it rewrites it as the derivative of something, so it can use this rule. And so the inverse of that term is this, but we need to invert this, so it inverts 3 over s plus 2, and it puts it all together and says the inverse is this. Now this sentence appears to be the same sentence that we saw up here. All right, it appears to be exactly that sentence. But what comes after that repeated sentence, which I highlighted in color, is not the same stuff. Maple is simply saying here, if you take the inverse of this, you are going to get this, which is what it just ended up with. So it's simply a restatement of results, and it's continuing now to tackle this non-homogeneous part. And it looks at it as a convolution. It says, okay, we have a transform here multiplied by 1 over this polynomial. So it looks at this as a convolution between these two things. If you invert this piece, you get f of t. You want to invert this piece. It tackles the inverse of 1 over s plus 2 squares by looking at it and saying, oh, I can see that as the derivative of this, and it uses the derivative rule. It needs to get the inverse of this piece. It gets that, puts that stuff together. So it now has the inverse of 1 over s plus 2 squared. It's this term. Now it's going to build the convolution. There you can see the convolution. It sets up the convolution integral. Needs to consider these integrals. It now says, okay, the forcing function was e to the 2t, so it's e to the 2 tau, puts that in place, computes the integrals, simplifies, and it now can write down the solution to the initial value problem. So this is a solution stepwise, and it really gets down to primitive techniques. Probably it would be up to the individual instructor to decide to what extent those by-hand techniques are essential to learning this material. Our 7th example has us take a look at a series solution. Differential equation, non-constant coefficients, series solution. Maybe Maple could solve that exactly. We're going to solve it by series. So differential equation, go here to the Student ODEs, solve, you have series, and you have series with steps. When you invoke that, this is how Maple proceeds. So we're going to solve this equation. You assume a series of this form. Okay. You need to put that assumption into the differential equation. So Maple says, okay, let's worry about this term first. Then it worries about the derivative, a second derivative. Puts the pieces together. There's x to the k. See, it kept x to the k here because it made the shift here. So sum from 0, x to the k, x to the k. The coefficients must be identically 0. And so it says, here is what the solution would look like, but the coefficients are given by this recursion relation. Does not give you, at this point, all of the coefficients. It gives you this recursion relation for the coefficients. Well, can we take this recursion relation further? So let's take a look. Grab this recursion relation, control drag it, bring it down here, give it a name, and apply Maple's solver for recurrence relations. Now, these are subscripted A's. And if you were typing them out, you would use a square bracket, A with a square bracket, K plus 2. The rsolve command is functional. You must use round parentheses. So you can control drag it, but you've got to change subscript notation to functional notation. And Maple solves this recursion. It says you will get this whenever k is even and this whenever k is odd. So all of these will be multiples of A0 and all of these will be multiples of A1. So you're going to get two different infinite sums. You're going to get two separate solutions. Well, let's see what S looks like when you put even numbers in. So 0 to 10 by 2, so you can get 2, 4, 6, 8, 10. Everything is a multiple of A0, 1 over, you can see what the coefficients are. And then you do 1 to 11, and you go by 2, you get 1, 3, 5, 7, you get the odd ones. And so you get everything is a multiple of A1, and you get these coefficients. Let's set A0 and A1 both to 1. So I do that here. And then simplify the result. So I'm really simplifying this thing after A0 and A1 are 1s. Let's assume K even, and we'll call that result A. And replace K by 2K, so we get the even coefficients. And let's replace here K by 2K plus 1. So this is what you get when you assume K is odd. So we're splitting this up into its odd and even terms. So A will be this, big A will be this, and big B will be that. What do some of these coefficients look like? So we make a sequence here, you get these numbers. You make a sequence here, you get these numbers. With those coefficients, you can make a partial sum. So add A x to the k here and bx to the k here. You have a partial sum, you have a partial sum. So this is what the two linearly independent members of the fundamental set look like. This is what they look like if you sum to infinity. Lo and behold, Maple sums this series to e to the e to the minus x over 2. E to the minus x over 2. And it sums this series to a multiple of the complementary error function. Wow. I wonder if those are actually solutions of this differential equation. If you expand e to the minus x over 2 in a power series, you get the terms that we had here in this partial sum. If you expand this multiple of the complementary error function in a series, you get these terms which match these terms. So progress has been made in obtaining a series solution, and the stepwise presentation does show what steps have to be taken. It does not show how to put these things together. It does not show you which Maple commands will do things like shift the index, but it does show you what has to be done. For an 8th problem, we're going to do a perturbation series solution. Okay, so here is the differential equation. Y double prime minus sine of epsilon y equals 0. Simple initial conditions. In order for this solution to appear correct, we must minimize the font size. Right here, you bring up the Student ODE package. And in solve, you find perturbation with or without steps. So I pick with steps. This pop-up shows up, and I write in the initial conditions. Well, this box isn't quite big enough to show that y at 0 is 0, but y prime at 0 is 1. Parameters epsilon, I'll go up to third order. So I need maximal width. And you'll see what happens if I do not shrink that. So let's go through this solution. And let's see, I think I can magnify it until I get to the critical spot, so you can read this thing better. Okay, at the critical spot, I'll just show you what happens if you don't shrink it. So Maple says, we're going to solve this problem. It's going to take an expansion of this sine term in powers of epsilon. And so you now have the differential equation y over prime plus y, and then this is expanded epsilon y cubed over 6. And the equation is rearranged, and it says we're going to try a Poincare Lindstedt perturbation solution. Actually, it's a Lindstedt perturbation. A Poincare solution ends up having secular terms, and the method, Poincare method, does not deal with the secular terms. It's Lindstedt's technique that gets rid of the secular terms. For some reason or other, Maple has used this phrase. Okay, so what do? You assume y has a solution in powers of the parameter epsilon, but you must expand x as omega times x. It's easier if you keep this as the new variable. Now, that's the Greek letter for t. Tau or tau, I don't know how to pronounce it. I'm going to say tau. And omega is itself expanded in powers of epsilon. So you put all that into the differential equation. There's your second derivative, third, second derivative, second derivative. And now these are derivatives with respect to x, but you need derivatives with respect to tau. So you replace the derivatives with respect to x with derivatives with respect to tau, and you pick up these powers of epsilon. So there's your differential equation. And you begin to group with respect to powers of epsilon. So the epsilon equals 0 term looks like that. So you now are going to solve this differential equation for y0 of tau. And here's where you use the inhomogeneous condition on the derivative. And Maple backs up and it finds the characteristic polynomial, characteristic roots. It gets the first solution, cos tau, and second solution, sine tau, puts them together, makes the general solution for that problem. It checks the validity, makes sure it satisfies the initial conditions, and that requires that you calculate these two coefficients, and you end up with the solution to y0. Knowing y0, you can use that in the equation for y1. And that equation for y1 will look like this. Now, if you realize that the homogeneous solution is going to have a sign tau, and the driving term has a sign tau. So the solution to this equation is going to have tau times sine tau. And that's what's called a secular term, because as the variable tau increases, these oscillations will get bigger and bigger, and that's what's called a secular term, and it just ruins the validity of the perturbation scheme. So you want to choose this omega so that there is no secular term. So a little bit of algebra here, you factor, and you realize that if you set omega 1 equal to minus a half, the right-hand side will be 0, and you will be solving this differential equation with homogeneous boundary initial conditions, and the solution for y1 will be 0. So now you go on and you look for the coefficient of epsilon squared, and that's the differential equation that you end up with. And you again realize, look, this is going to have sine and cosine as solutions to the homogeneous equation. And this is going to pick up a tau sine tau. So you're going to get a secular term again. In order to have that drop out, you make this coefficient be 0. So omega 2 is minus 1/8. You are now solving this differential equation with this homogeneous data, and y2 is 0. That allows you to pick out the epsilon cubed coefficient, which is this differential equation needing to be solved. And here it's not clear whether or not you're going to get secular terms. A little bit of trigonometry puts this right-hand side into this form. And in this form, you see that if omega 3 is 0, this will kill off a secular term. This does not generate a secular term because this is not a repeat of either a sine or a cosine. So you set omega 3 equal to 0. You solve this differential equation with homogeneous initial conditions, and it will turn out that y3 is sine cubed over 48, which means that you can write the solution in terms of tau as sine plus sine cubed epsilon cubed. And this is what tau will look like. This times x. And so the differential equation has this for the solution in terms of x. Right? See that tau is replaced by this, and it's here. Again, in the sine cubed, you get this. All well and good. Now, look at what's down here. It's a repeat of the solution that we just saw. If we shrink that, then that goes away. So there's a little glitch here. They're working on it. And then you ask yourself, how good is this perturbation scheme? And so I set epsilon equal to 0.2, just pull a number out of the air. This is what the solution looks like when epsilon is 0.2. But in this equation, epsilon is set equal to 0.2. And I solved that problem you see it in green. In red, I did a numeric solution, and I'm out here to 20, x equals 20, and that looks like a pretty good approximation, and that's why this method has survived in the literature. For our next example, I think I'll restore the magnification here. Let's implement undetermined coefficient. So we're going to find a particular solution for this differential equation by the method of undetermined coefficients. What Maple is doing here is looking at this right-hand side, and it's saying, let's try that term as the template for the particular solution. And if that's the case, you got to make sure that this is linearly independent of the solutions of the homogeneous equation. If you look at the homogeneous equation, it's m squared 4m plus 4, 0. So the characteristic roots are going to be repeated. It's a repeat of minus 2. So Maple says one solution from the homogeneous equation is e to the minus 2x. A second one would be x e to the minus 2x. And if you take the third one in the form e to the minus 2x and compute the Wronskian, you're going to get 0. Now, it doesn't show you that it's 0. It just says not going to work. So it says try over here putting an x. Well, if you do that, you can see you're going to get another Wronskian, and it's not going to be non-zero. So he said, Maple says, well, try an x squared. So that works. And your particular solution is therefore a multiple of x squared e to the minus 2x. Put that into the differential equation. Figure out what that coefficient C1 has to be. It turns out, for that an expression of this form to be a solution, that coefficient has to be 1/2. So it ends up with a particular solution of x squared e to the minus 2x over 2. It is this unusual approach to determining what the guess here for the right-hand side should be that caught my attention. Make a guess and just test it by computing the Wronskian. Now, there's a command in Maple to compute a Wronskian, and you can easily determine whether that's identically 0 or not. I think I'm going to jump to example 11. Example 10 is going to take us a bit of time, and if I have time at the end, I'll come back to it. So 11, we do a change of variables. So here's a differential equation into which I want to make a change of variables. And the change of variables that I have picked here to illustrate is to substitute for y sine, which is a homogeneous solution, times an unknown v. And you'll notice here I have an x, and here I'm using t, and I have to include this statement, x equals t. And I got this pop-up by going here to the context panel, Student ODEs, change variables. And you get that pop-up, and you fill it out as you see here. That results in this differential equation. You'll notice this is a v prime, this is a v double prime, which means we can make another change of variables. We could call this w, and this becomes w prime. So there's your w, and there's your w prime. So I'm going to make that second change of variables, and you do it the same way. And here, the derivative of v of t with respect to t is now called w of x. You go back and you set t equals x. This differential equation has been reduced in order. And if you look down here, the next thing we're going to look at is reduction of order. So these changes of variables are linked to the idea of reduction of order, but it illustrates how you use the change of variables command. So here's w. We've solved the dE. You just call for a solution of the dE w. V is then the integral of W, and I have set this constant to 0. So this is the integral I have to evaluate, and this is what I get. And if you look here at the solution of the original differential equation, the piece here is the particular solution. And if you take this V and multiply by that sine x, then the cotangent becomes cosine. So this term is this term, and sine times log sine is this term. So this device has produced the particular solution. Now, what I just showed by changing variables is really an example of this reduction of order. And there's a command for that. But here's the theory. It's exactly what we illustrated above. You have a solution of the homogeneous equation, and you want to find a particular solution, and you look for it in the form of a product of the known with an unknown. You run that through, it reduces the order, you solve the reduced equation, you get the factor, multiply by it, so forth. So we just did that. And here is that same calculation done with Maple commands. Eval to make the substitution UV. Eval to change V prime to W. Desolve the equation, integrate to get W, multiply by, integrate to get V, multiply by sine x, which is the product UV, and then compare that to the particular solution that Maple finds. Now, let's do that with the tools of the student package. Okay, here's the differential equation. Student ODEs. Reduce order. And it says reduce order to get a linear particular solution. That's what we've just done. Okay, so the return is this pair. This is the reduced differential equation. Notice that it jumps down to the W because that's what you put in here in this pop-up. The known solution sine x and the variable in the reduced equation. And this is the pair of transformations that you have to make in order to get down that far. So here is the differential equation. Now you need to pick this off. So you use, in the context panel, select element, and you take the first one, pick number 1. Okay, you got the differential equation. Then you can solve this, just get the solution. Okay, here is W. You want to set this constant equal to 0, so you can use evaluate at a point W. That's really V prime. So you do the integral, that's V. So sine times V is the particular solution. And notice here this word solve, and this drop down is set to false. So in other words, don't solve. Let's see the steps of the intermediate equation. If you say true, then when you do this reduction of order step, you will immediately jump from the differential equation to the particular solution. Now here are 2 techniques that I can remember from Rainville's differential equations book that I used 60 years ago, and I kept that book and looked this up several times over the years to make use of one of these techniques or the other. If you have a differential equation, second order differential equation, that does not have the dependent variable, there is a reduction of order technique that you can use to get a solution. So here's this example. Differential equation. So you have derivative, derivative, derivative. There's no actual y. So what you do is you write the differential equation and you invoke this reduce order, and Maple says, oh, this is the case that has no dependent variable. Very good. And so the pop-up here requires that you put in the name of the new dependent variable. And keep an eye on this. Don't solve the equation. Just return this reduced equation and also these transformation equations that get you from here to here. I gave this sequence the name Q so that I could reference the first piece. This is the differential equation, the reduced differential equation. And then you hit it with the appropriate solve, and you get this pair of solutions. I've called this pair W. Let me try and keep that on the screen. Okay, so here I've used the evaluation template. Here, you probably recognize that from here. I've got it here. Evaluation template, and it comes out of the expression palette. So I want to evaluate the first member of W, that's this one, using these transformations, these equations of transformation. That's what the second part of Q is. So the U becomes Y dot, which means you have an integral here you can evaluate. So you hit it with the integrate, and there's a integrate in the context panel. You get this form of the solution. And then you take the second solution here in W, and you evaluate it with these two equations, and you get this differential equation, which it's just an integral, and you integrate and you get that. Now, if you look at those carefully, you can put this one into form t squared plus b minus y squared as a constant squared. And here it turns out it's y minus b, but these are equivalent, so the solution is really a circle. So if you go directly to the differential equation and you ask for the general solution, you get these two things back. If the differential equation has no independent variable, there is a reduction of order technique that works there. So here's an example. It has y and derivatives, so it does not have a t. So there's no independent variable. Context panel, student ODEs, reduce order, no independent variable. And you need to tell Maple the differential equation is an equation in y of t. And this is the pop-up that you get. You give the name of the new dependent variable, and I have chosen not to solve the equation because I want to see the pieces. And the return is this sequence, reduced equation, and the equations that reduce that given differential equation down to this. This sequence has the name Q. And I've switched here to a couple of commands just to expedite the exposition. Solve this differential equation. That's what Q1 is. It's this piece. And you get two solutions. Then make these transformations to return back to y, and you do that in both of these. So we have two of these equations to look at. Turns out there's a y prime, a y dot, and a y. These are variables separable. So separate variables in this one over here, and separate variables in this one over here. And once you separate variables, then you can integrate both sides. So hit it with an integrate, and you get this expression, you get this expression. Do a little algebraic massage, and you realize that you're looking at a circle. Now I've got just a few minutes left, so I'm going to jump to the problem I skipped, is number 10. Let's close up some of this stuff. And I'm going to do just one piece of it, this one. System. Interesting thing is that the matrix is deficient. Take a quick look at what the steps are. You get a first eigen solution, and then to get the second one, you make this assumption that the second one looks like this. P is the unknown vector, v is the known eigenvector. Okay, you push it through, you get P. Now you have two solutions. From the two solutions, you can get a fundamental matrix. If you have a fundamental matrix, you can solve the initial value problem, get this solution, and here I've checked it against a D-solve. So here's an example where you don't need to know much about Jordan form theory. You follow this algorithm, and you would get a solution to this 2 by 2 where the matrix is deficient.